Okay, so last class we discussed about transistor. We know transistor have different regions, and we compare the length of those regions also and doping of those regions. For example, uh, yes, this is the transistor. So we have different regions: emitter, base. This is base. Base is very thin, and it is also lightly doped, right? So okay, so this is emitter. Emitter have a lot of emitter have a lot of charge carriers. So it has a lot of electrons in our case. It's a NPN transistor. Let's say it's NPN transistor. This is N, this is P, this is N. Okay, so this is a NPN transistor. So it has a lot of electrons in the emitter. So this is emitter.
Sir, screen is not visible.
Oh, sorry. Okay, sorry. So fine. So this is our transistor. This is emitter. We have base and collector. So till now we have discussed is in NPN transistor. We discussed this is an NPN transistor. You can see the current direction. So you can see the current direction. It is flowing from like a diode. This is the current direction. So current always flow from P to N. This is P. So this is N. P to N. So the third uh, region is N. So this is NPN transistor. So this is emitter part. So this is base part, and this is collector part. So we know the equation. Emitter current is the maximum current. I emitter equal to I base plus I collector. So this things we have discussed. So this is the emitter current IE, and this is nothing but sum of base current plus collector current, right? So this is NPN transistor. So we have base is slightly doped. So here this P-type region, it has slight holes here, and we have a lot of electrons in the collector also. Okay. So here to operate the transistor, we need to forward bias. Forward bias the base emitter junction as forward bias. So what I'm doing, I'm going to bias the base emitter region. So forward bias means P should get the P or the base region should be getting positive. So I'm giving a positive bias on the base and negative bias on the emitter. So N region is getting minus. So it is forward bias plus minus. So base is plus and is fine. So this is forward bias. So it's like forward bias diode. So this is emitter base junction is forward bias. Now what about the collector base junction? It has to be reverse bias to make the transition active region. So right now I'll connect this N to the positive region, right? And and this is minus, this is plus, right? So now we can see the collector base junction is reverse biased because this is N is getting plus and B is getting minus respective. Okay, so what are the other important things to be noted here? We discussed there's a current. The current will be starting from the this negative potential will be repelling all this charge here, that is N type, that is electrons. So they'll be moving to the base. Once they reaches the base, there are two options. They can either go to the battery supply voltage, the external circuit, or they can pass to the collector collector region. Now, because of two things we discussed, base is very lightly doped, so there is very less recombination in the base, and because of the very low dimension, less size of the base, most of the electrons enters the collector. They don't have much time also, right? Because it is very lightly doped and very low thickness, right? So it's most of the electrons enter the collector. So very less base current will be there, but it will be very less. Okay, so this is the condition. So most of the electrons enter the collector area. So IB is very less. Now another important thing is how we name the voltage source. Here V, this is B, VBE. We call it VBE, right? VBE because this is connected to the base and connected to the emitter. Sorry. VB. Now, what about the top voltage? This is plus. This voltage source is called V collector and emitter. So this is connected to the emitter piece. Okay. So these are the different voltages, and in all this discussion, we use V capital, B capital, E. These are the junctions, base emitter, and V capital means DC. What about the signal? If we are talking about a signal, it is small v, small letter v. V and AC signal, VB, something like that. VB. Okay. So I think this much we have discussed. Now let's plot the different graphs. I think we should plot different graphs. So let's draw it. So this is our transistor, emitter region, less size, heavy doped, base region. We will take NPN for the all exams, NPN transistor, and we have a lot of electrons here, and I need a base resistance to control the current. So I use a resistance here for RB. RB. Now I name this supply voltage individually. I call it VBB because I'm giving it to base VBB, V base bias VBB. Okay. Now I also keep a collector current to control the collector current RC, called RC. RC, and this voltage source I name as VCC. VCC. This RC. Okay. So now there are some voltage. As named the supply voltages, V supply voltage VBB. I'm giving the supply voltage entirely to the base, so I call VBB. I'm giving the supply voltage to the collector again, so VCC. Now, because of these two voltage, we get net voltage across base emitter. What the voltage? V base emitter. Now we can see that because of the resistance, the base emitter voltage is this. This is the base emitter voltage, VBE. What about this voltage? Starting from resistance here, VC, collector emitter voltage. This is the collector emitter voltage. Okay, I'll not mark the regions here. This is definitely collector, collector. This is emitter, and this is base. Okay, so now we should plot the different characteristics, that is transistor currents versus different voltages, right? So before that, I think you know what is alpha and beta. Beta, I think we discussed, is a DC gain. DC beta is DC. Beta, what is beta? The ratio of the collector current to the base current. You can say beta equal to ratio of the collector current to the base. I think we have discussed this, or you might have already studied this. For current gain. Okay, so also called DC beta. It's also called DC beta. Right? It's also called DC beta or current gain. Right? It also tells how much the larger the collector current is compared to the base current. Usual range varies from, you can say, 100 to 300, something like this. This range is 100 to 300. Not these points down, because these are the common questions in the Viva and all. Okay, so maybe you can write beta DC, beta DC. Okay, and the beta values also varies with respect to the high power. If a high power transistor, it may have more or less values of beta, because okay, so that is the case of beta. What about alpha? What's the meaning of alpha? Alpha is the DC alpha. We call it also DC alpha. It is the ratio of the collector current to the emitter current. I think you already have studied this thing. Alpha, you can call alpha DC also. Collector current divided by emitter current. So we can see alpha will be always less than 1 because IC is always less than IC, and usual values of alpha ranges between 0.99 to 0.95, something like this, right? Because IB is negligible. That means you can see the ratio is nothing but alpha DC equal to IC divided by IE. It's nothing but IC divided by IC plus IB. But as IC is tending to be very less, we can see this value approaches alpha DC approaches around 1. This usual value is around 0.95 to 0.99, something like this. This is the usual values of alpha. Okay. In high power transistor, it may be a bit less, maybe more or less. Okay. So from these two things, we can derive equations for alpha and beta in terms of each other. Say maybe you have already alpha in terms of beta is beta divided by beta plus 1, and beta in terms of alpha is, I think, is alpha divided by 1 minus alpha, something like this. So these two things we can derive. Now there are three possibilities of transistor connection. So what are the three possibilities? So now we have discussed different kind of biasing. That means emitter base is forward, collector emitter is reverse, collector base is reverse junction. So that is one of biasing. And there are different possibility of biasing. We discussed we have around four different possibility of biasing. Two junctions. Each junction can be two type of biasing can be there. That is 2 into 4 types of biasing. But right now we have connection of transistor. Now, what about the connections of a transistor? Say for example, I have a transistor like this. How am I connecting the transistor with respect to amplifier or in circuit? How am I connecting the transistor? Say for example, I have 3 points. We have discussed this is emitter, this is collector, and this is base. Okay. Now, what are the three different possibilities? Okay. What are three different possibilities? I can connect my input and output with a common one terminal. For example, I can make emitter. I can make this emitter common between my input and output. Right? This emitter can be common between input and output. So how it works? Okay. So this how can I make this terminal common? Okay, so how can I make this terminal common? So I can give an input here. For example, I can give the input. For example, there is some input here, small AC signal which I'm going to amplify, right? And so I'm giving with respect to two terminals. What are the two terminals? Base and emitter, right? So I'm giving my input between the base and emitter. Now, what I'm taking the output from? I'll be taking the output from collector. This is the collector terminal and emitter terminal, something like this. Collector terminal. So this is my big output. I'm getting big output across these two points. Although I'm just symbolically representing these two things, but in actuality, this circuit doesn't work because there is no voltage. DC voltage is not giving. Okay, so but you can see the only one thing here is I'm keeping emitter as common between input. This is input and this is output. The only one terminal common between input and output is the emitter. So this is called common emitter. So this is called common emitter connection. Common emitter connection. Okay, this is called common emitter connection. Why the emitter is common between the input and output? Right. So common emitter. Now, likewise, what will happen if the common base? So with this common base, we can say a transistor connecting like this. Say this is base. Now, if I give input, if I give input across here, this point, this is the emitter, this is the base region, and this is the collector region. So if I give my input across this region, this is my input. and output I'm taking across this collector and base. So this is common what? Common base, because this is base is common between input and output. So this configuration is called common base. Although this is a symbolic representation, if we need to work practically, I need to give biasing all those things. I need to give DC voltage at all those points. DC biasing is required on all points. Minus plus. So this is forward bias, so it should be minus plus. Okay, and like this I need a biasing here also. So this is just representing common base. Now common collector, so this is common base, this is common base, common base connection. This I'm seeing the base is common between the input and output, right? This is common base. Now what about the common collector? Say if this is my transistor, so I need to give the input in this point, base and collector, and giving the input at this point, and my output will be, okay, my output will be taken across the the collector and emitter. Okay, so output will be taken across these 2 points. The output will be taken across these 2 points. Okay, so here we have, this is the base and collector. Input is across base and collector, output is across collector and emitter. So collector is common between these two things. So this type of configuration, common collector. Okay, so this thing is called common collector. Okay, now let's go into real circuit of common emitter and start plotting some graphs. Now I'm going to go draw a real common emitter, which is practically you can use it. So here, okay, so here I have the transistor, NPN transistor, and I give some base resistance to control the base current, and I'll give a voltage VBB here. VBB means voltage at the given at the base. Now I'm also connecting some collector resistance to control the collector current or the voltage drop here, and I give some voltage. So you can see this collector voltage is a bit greater than the okay. So now this is VCC as I described, VBB, and the base resistance RB, and the collector resistance is RC. Okay. Um, Now we already know the different voltage representation, because this is our base, this is our emitter, and this is our collector. Now what will be this voltage? This is VBE. VBE. That is voltage across the base and emitter. Now this is VCE, voltage across collector and emitter. This is VCE. This we already know. Okay. So voltage at the base I can call VB. So this point, the voltage at this point I can call VB, voltage at the base. And this point VC. And this point I can call V. I already told you what is DC, how DC representation and AC representation differs. Okay. So what is actually VBE? We can from this diagram, you can easily understand that VBE, voltage across base emitter junction, is nothing but VB, voltage at the base minus voltage at the emitter, right? Likewise, VCE is also voltage at the collector minus voltage at the emitter, right? Okay, what is V? Now what else? I think, yeah, both voltages. Now what is 1 minute? Okay, so Now, if we reverse VEB, we can just reversing the direction of looking VE minus VB. Okay, we are just reversing the direction. So VE is the voltage, DC voltage at the emitter. VB is the DC voltage at the base. Okay, fine. So right now let us try to plot the base curve. What is a base curve? There are two input characteristics and output characteristics. So let's try to plot the input characteristics of the common emitter configuration. Okay, so let's change everything. Now, for that, what we need to do, we need to measure the different voltages and currents in this configuration. So, what we will do, we first of all we will be interested into changing the voltage. This VB we are interested in changing. So, VB I'm putting a variable voltage. So, based on the variable voltage, I'm much interested in measuring the current. So what I'll do, I will take an ammeter and I keep ammeter here. So I'll keep an ammeter here so that I can know how much current I am able to pass into the base. RB. Okay, so based on these two, also obviously I need to have a voltmeter also, which measures the how much voltage I am giving here. So there are one. Now you can see both I'm keeping in the input region. You can see this I'm keeping in the input region. Okay, so the best option here basically I need not have the voltmeter on the VBB. This is input voltage. VBB I'm keeping a potentiometer and input voltage. But what I'm more interested in keeping a voltage source, sorry, a voltmeter at V base emitter junction. This is what actually I want to measure, right? So I don't need to have a volt source here because I already have a variable voltage source potentiometer there. So I leave that there. So this is the best VBB I'm wearing, and I'm measuring the VBE, and I'm also having measure ammeter to measure the IB, right? So I'm changing the VBE by changing the VBB. Can change the VBB, and after each variation of VBB, I can measure the current, ammeter current, which is nothing but IB. IB. Okay, so starting with 0, I'll measure the VBE, then I measure the current. I know when the voltage VBB is 0, I will not have any. 1 minute. Okay, mm, so you can see the characteristic you can assume. You can see this is nothing but a diode. You can see the base. The base emitter is nothing but a diode actually. You can see here, it's a diode. So nothing but we are trying to find the curve of a diode, which you already know. I know that you already know the curve of a diode. That's exponential curve. That means we are plotting IB. This is IB base current versus base VBE, base emitter voltage VBE of a transistor. Now what we get initial VBB is 0. I'm giving 0 potential, so obviously the voltage drop will be 0. Again slowly I increase the VBB so that more VB drop will be there. So we can see the graph like this. You can see the graph initially it was very slow and particularly sorry. So this is my graph, and now I'm plotting the. So initially it becomes 0, and at knee voltage it becomes like exponential, right? So this is my IB versus VB. Now what is the knee voltage? You already studied that this is 0.7 of a diode. So beyond this point, it increases exponentially very high. Okay, so this is about my input part. Now let's have some equations of IB. Let's try to mathematically see what is the equation of IB. So we can see the IB is nothing but IB is controlled by the RB. RB is controlling IB, and the voltage drop VB is controlling the IB. So we can understand that IB, current passing into the base of a transistor, is nothing but the voltage source which is pushing it, VBB. That's nothing but VBB, and the voltage drop across the base of a transistor minus VBE. You can say they're an opposite polarity. VB divided by RB. Is it clear? So this is the base current equation. First VBB, just pulling what is source. VBB is pushing the current. Minus, this is plus and minus. This voltage drop is plus and minus. So this is minus VBB minus VB. This voltage drop VB divided by RB. This is the equation of IB. You can write it nicely. IBB equal to VBB minus VB divided by RB. Right? You can see if the voltage drop is zero. In ideal transistor, we know VB is zero. So we can see just ideal transistor is VBB by RB. Definitely, but in real transistor, we know this is zero point 0.7, VBB 0.7. So we can see in real transistor, one practically we know VBB minus a constant zero point 0.7, zero point 0.7 divided by RB is the base current. Okay, there can be some problems, but we'll do problems later. Okay, so this is about the IB versus BV input characteristic base curve. You can say this is base curve. Now we are interested in the this is transistor, so base resistance and a base voltage. Again, now we are interested in the output characteristics. This is voltage VCC. Now we are interested in varying this voltage. VCC we are interested in varying. Okay, so either we can use RC also to vary, but usually we keep RC fixed. Okay. Now what we are going to measure? Now we are going to measure the V voltage. We are keeping a voltmeter across the collector and emitter part of our transistor. Now we are also interested in measuring the collector current. So we keep a ammeter also. Measure the IC. So the IC and VC. This is collector, this is emitter. So we are interested in measuring the voltage across VCE and the current passing through the collector and emitter, this current IC. Okay. So if we plot one starting with zero voltage, we can see now there is a one question when we are plotting this thing. There's one question here. What we are going to put our base? This is one question. In what voltage and what current setting we are going to put our base again? Now, that is a very important question. Are we going to give sufficient VBE or not? Plus minus. That is another question. Are we going to give sufficient VBE or not? Okay, so the answer is yes, we are going to give sufficient VBE so that the transistor is on. If the transistor is off, that means VBE is less than 0.7, there is no point of giving any VCC. Because transistor is not on, there will be current will be less. IB will be 0. If IB is 0, IC will always IC will also be 0. So we have to keep the VB more than 0.7 something. Or we can should give some IB should be there. Okay, so let's put VB some, we'll give some VB some value so that we are giving some IB. For example, we are putting IB equal to 10 micro or something. For example, I'm just setting 10 microampere. Okay, so that we'll give that much VB so that there is some IB, so that we can plot different VC and IC characteristics. Okay. Okay, so now I'm going to plot this. Maybe I'll draw here. Okay, now if I'm plotting this, this is IC, this is VCE, this is IC, this is VCE, right? So I'm going to vary VC and I'm checking the IC. So what I'm going to get here is initially it's linear. Initially I get a linear curve. It's linear curve. As VC increases, IC increases linearly, right? Why? Because of the resistance RC. Because the transistor is also acting as a simple current source. Sorry, not here. It is not current source. It is just linear resistance. The transistor current is also increasing, and because of RC, I'll get a linear curve. The resistance curve. If you have only resistance and voltage source, you'll get a linear curve. So I get a linear curve initially. Now, after some time, the transistor gets saturated. That means the amount of current which the transistor can carry, that is ICE or IC, is becoming saturated. Why? Because we know IC equal to beta times IB. So we already have set some IB. For example, we have set IB how much? We have set IB equal to how much? 10 micro, something, any value. I'm set already 10 micro. So based on the beta of the transistor, my IC is having a values, a constant value, depending on the beta. If beta is 100, it is 1 milliampere. If beta is 500, it is like 5 milliampere. So like that. So that current is going to reach. That current is called saturation current. So right now, what happens is I increase the VCE. Now the current is not going to increase; it is going to be constant. So it's called saturation point. Now if I again increase the VC again at one point, if long increase in VB, it's going to the breakdown region. It's going to break down because the transistor is going to break down. Why? Because of the high voltage or high electric field developed across the collector and emitter. So that is we don't want the transistor to operate at breakdown region because it gets burned. A lot of heat and light is generated and it gets burned at this point. So I don't care much about breakdown region. I'll always operate in active region. So what is active region? This is the active region. This is the active region. Active region. This is the active. This is the breakdown region. Breakdown region. And this is the saturation region. Saturation region. So I want to operate my transistor in which region? Active region. This region is active region. Or in general, we can say you want to make the transistor work in a region where collector current is saturated. It acts as a current source. Okay. So we are working in active region of the transistor. Okay. And where is the cutoff region? The cutoff region is this is cutoff region. There's no current, there's no IC is not there. So this is can say cutoff region. Okay. So breakdown region is dangerous. We should not operate in breakdown region. We should operate less. Uh, so it depends upon the current rating and voltage rating of the transistor. If the current rating and voltage rating very high, that means the transistor can operate in very high voltage and breakdown region is far away. Right? That is obvious. So you should design a transistor. You should use a transistor whose wattage means power handling capacity. Wattage is sufficient. Okay, and you should always use the rated current. You should always know what is the rated current of a transistor and how you'll get that. You'll get in data sheets. So data sheets or those manual where the company which designed the transistor or fabricated the transistor will be giving you free of cost. It is available openly available in the internet. Just type the name of the transistor you're going to buy or bought, and you'll get all the characteristics of the current, voltage, power, temperature variations, current gain, alpha, beta, all those things in that transistor manual we call data sheets, right? So here now we should remember this is for a fixed IB. We have set the VB. Here we have set the VB also, and we have set special IB. Now if we vary this, we'll get another curve with the different VCE and IC in a different direction. So I'm going to change the IB a bit higher. So what the new curve I'm going to get? Something like this. The new curve I'm going to get like this. If it was something BT was something IB was something less, it will be something like this. Okay. Again, if you can increase the IB, something for is going to go higher like this. But you can see the breakdown region is which like reducing. You can see that is because more current my transistor is conducting at a higher voltage or same voltage. That means the power is handling is high. My power dissipated by the transistor is high, so it can break down much easier than lower current regions. Right? So this is current is maybe this is 10 micro. Now this is 20 micro. This is 30 micro. This is 40 micro. So as I'm increasing the current, base current, you can see my IC saturation is going to increase. At the same time, breakdown region is going to decrease also. It's coming nearer and nearer, breakdown region nearer because the power handling, the power dissipation capacity of transistor is limited. So as high current is flowing, my transistor will get faster breakdown. Okay, so that's about the collector curve. Now, the equations in this region, first of all, I have told you that VB, base part we have fixed. We can fix the base current by fixing the VB and RB, right? That we already seen. Okay, now what about the collector equation? Now, the collector part is controlled by the VCC. Yes, VCC is driving the current to the collector, and RC is also controlling the current. And the voltage across VCE is also going to affect the current. So we can see from this equation from here, I'm going to write the equation, current equation in the bottom. That is VCC across the transistor is drop across IC into RC according to Kirchhoff law plus VCE voltage across collector and emitter terminals of the transistor. Okay, so this is the collector part KVL. So from this we can see what is IC. IC is nothing but VCC minus VCE divided by RC. Okay, it's self-explanatory. These things are very important. You just write it down. VCC equal to ICRC plus VCE. That means VCC applied voltage is driving current IC, and this voltage will be dropped across ICRC and VCE, the base emitter resistance, collector emitter resistance of the transistor. Okay. So this, based on these two equations, now we'll do some kind of problems. So before that, I'll clear what is cutoff region. What is the cutoff region? Cutoff region is that region where the transistor is not conducting sufficient current. For example, uh, say, this is the curve VCE, this strong V collector emitter voltage. So we already discussed different region, different base, based on different base current. I have this is less base current. If I increase the base current, I have better. Again, increase the base current, something like this. Sorry, I can go on increasing this thing. So here this is breakdown region is also using. Okay, so although ideally this region should be much to the right, so I'm just drawing here. Although we need a lot of voltage swing. What is swing? This is the range where the voltage my transistor can operate in VCE. So this region I can call a swing, where my voltage can swing between the VCE range of voltage. Maybe this is 2 volt, and this is 4 or 4 volt, something like this. Maximum voltage is 5 volt, right? So this 2 to 4 volt, my voltage can swing. My output voltage can be appear any point between 2 volt and 4 volt. So this is the swing where my output can be swing. Okay. Now what is the cutoff region? Cutoff region when the transistor is not properly on. So cutoff region is this is the cutoff region. This is the cutoff region. Cutoff region. This now IB is very less. Here IB is 10, 20, etc. But at the bottom we can see IB is very less. This means not sufficient to the conduct. So this is the cutoff region. Cutoff region. Okay. So this is cutoff region. Now that's all. We'll do some problems. So I'm just giving a problem. So we can do some problem. Right? And tomorrow we'll continue with the DC load line. So I'm going to draw it. This is a transistor. This is some resistance here, some VC here, and this is the emitter, and this is some RD here, some voltage here. So now this is VBB, and the terms you have to remember. This is VBB, VBB, VCC, RC, RB. Okay, so let's say this is 10 volt. Let's say VC is also 10 volt. Both are 10 volt. Now this is RB is very high because IB should be less 1 mega ohm. I'm giving 1 mega ohm. What is mega? 10 raised to 6. 10 to the power 6. Why? Because I need very less IB. So I just give very high voltage there. And RC is 2 kilo ohm. I don't need much drop across this resistance. Why? Because my output voltage across collector and emitter. This is the most important voltage which I'm interested in, where my output voltage is laying. Okay. So now you need to find all the voltages, VC, base current, IC. So we need to find these all those things. We need to find IB, we need to find IC, we need to find VCE. Okay, VB you can assume definitely zero point 0.7 is already by default. We can know that's zero point 0.7. Okay, so this is the main thing: IB, IC, VC. These are the main operating regions of a transistor. So basically, if you see the operating regions of transistor is it is in the output curve, that is IC versus VCE curve, and that is my output. That's very important for me. That is where my output is, which I'm interested is lying. Now I don't want anyone to get confused. We are not given any signal to the transistor. Right now, we are given only DC value. Is the DC value our signal? No. We are not interested in changing the DC parameters. DC voltage and current I can easily make in any way using voltage dividers, using current, using resistances. So right now we are just trying to understand the DC operation of a transistor. We are not given the signal till now. Very important point. We are not given any signal for the transistor to amplify. Okay, so we are just giving understanding the DC operations of a transistor. So don't get confused. This is the amplifier. No, this is not amplifier. We are just giving some input volt. We are only playing with DC voltage. You can see there is no AC signal till now. Transistor amplifier is not for amplifying DC. Amplifying AC is our ultimate aim. Not AC in the sense signal, a micro signal, nano signal, since a signal coming from a sensor. It can be nano current, nano voltage, micro current. So it is small signal AC, or fluctuating some signal, maybe voice, maybe some light signal, maybe some anything, any slight signal from a sensor. That is what we are trying to amplify. Here it is a DC. We are only uh, discussing about DC part here. So that is a very important point. Okay, now let's analyze. Now, how we start analyzing? We need to find IC. The only way we need to find IC is equal to, we know the equation of IC. You know, IC is equal to beta times IB, beta times IB. So now the question how to find IB. Now our question is how to find IB. We know IB equation. IB equation is nothing but IB equal to, we know VBB minus VBE divided by RB. This is my IB. So from this I have given, from this circuit I have given VBB, VBE, RB is also given. So I can find the IB, right? IB is nothing but 10 volt minus 0.7 divided by RB. Okay. So if we calculate it, we get IB equal to 10 minus 0.7 divided by 1 mega 10 raised to 6. So you can say this is around 9.3 microampere. 9.3 microampere. That is IB. Now, okay, now you may ask what is the beta? Yes, beta. I'm giving a beta. In the questions like this, I'll be giving beta. For example, beta is 300 here. So now I can find IC. IC equal to 300. That is beta into 9.3 micro. 9.3 micro. So I'll get beta around, you can say here it will be around 1 milliampere, less than 1 milliampere, but around 1 milliampere. Not 1 milliampere, 3 milliampere, around 3 milliampere. Because 300 into 10, that means 3000 micro means 3 milliampere. Okay. Now we got IC. Now after finding IC, now we got IC is equal to around 3 milliampere. Now if you find IC, now we also given 10 volt. VCC is already given. So we can easily find VCE. We can also find the voltage across collector and emitter, VCE. So what is the equation? So VCE equal to VCC minus voltage drop across the RC resistance, right? So we know VCC is 10 minus IC is around 3 milli. I'm just taking an approximate value 3 milli into RC. RC is 2 kilo ohm. 2 kilo. So from here, you know the kilo is 10 to the 3, milli is 10 to the minus 3. So these two cancel each other. So we can say the net is 10 minus 6, a bit less than that because I'm approximating 3 milli, although the current is less than 3 milli. So you'll get 4 volt. So this is my collector emitter voltage. Now, what is the importance of this thing? Just getting an answer doesn't have any meaning in analog electronics. You need to have the feeling. What are we trying to get? Now, with this, we note this point. 4 volt is my VCE, and the IC is around 3 milliampere. This is very important things in a transistor. These two things. So I'll keep this thing, which is I'm interested in. and I'll delete all other things. Now I got the operating point. This is the output range or output voltage, which my output is still. You should remember this is DC. This is not AC. We don't have any AC signal till now. This is only a fixed voltage, 4 volt and 3 milliampere. Now, what is the importance of this? Let's see. Now, this is the IC. This is the VC. Again, we come to the output characteristics. Okay. Now, we can see there will be different curve. There will be different curve for different IP, something like this. The different curve is there. From this, we know a particular curve where IB, where our IB was how much? IB was around 9.3 micro. Our IB was 9.3 micro, 9.3 micro ampere. So corresponding to that IB, I'll get a curve here. IB is 9.3, so something like this. My curve is like this. So my IB, this is my curve. My IB is in this circuit 9.3 micro. So based on this curve, my saturation collector saturation current will be like this. This is how much? 3 milli, around 3, or I'm approximating here 3 milliampere, right? So this is the point, and this is the curve I'm interested here. This is the curve my transistor is now right now operating. And now exact voltage, we also got 4 volt. So if you plot the voltage in the x-axis, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 10. So 10, because of maximum voltage is 10. Now we know this is 4 volts. So this is exact point my transistor is operating. So this is the point. What is the point? 4 volt and 3 milliampere. Although this is approximate. So this is the collector voltage, collector emitter voltage, and collector current. My transistor is operating at this region. So this region is very important. And what is the importance of this region? Now, when your output point is fixed, that is 4 volt and 3 milliampere. Now, when some signal is given to the base part, base emitter part. So what happens? When some small signal is given to the base emitter, IB is going to change. Now IB is 9.3 micro. So if our IB has getting some change because of some signal I'm giving in the input, why is the input? So the AC signal given to the base of the transistor or the circuit is going to change my IB slightly. So signal, this AC signal plus IB DC signal. There is some fluctuation in my AC in the DC in the IB. Maybe my input signal is nanoampere, 100 nanoampere or nano volt or something, which is going to fluctuate my IB. Right now, IB is going to change. Right now, IB is going to change slightly in a nano level. Now, because of change in IB, IC is also going to change. My IC is going to change in a bigger way, right? So my IC is also going to change because IB is changed. Now IC is beta times IB amplified IB. So the IC is also going to change. Maybe it is going to change from this value to this value. So now IC is also having the change in IC is significant right now. From this to this, IC is changing. At the same time, VCE is also changing. VC will be changing from this to this point. So I know, and all those changes will help me. And so this is going to net change. So, sorry. So I wrongly drawn this. So net change I can draw in a like this. So what does this means? My IC is going to change. My VC is also going to change because if IC changes, VC also changes. And why IC is changing? Because IB is changing. Why IB is changing? Because I'm a signal giving an AC is fluctuating signal in my base or input transistor. This variation, maximum IC I'm getting. This is maximum IC. Maybe this is 4 milli or something. And minimum IC I'm getting. Maybe this is 2 milli or something. So this is my variation in my this is my variation in my collector curve, collector characteristics based on the input signal. So the thing, if you plot nicely, you can see this is the output I'm getting. VCE is also changing. AC based on the input signal, I'm changing my VCE, and based slightly I'm getting its output current also here. So this is also fluctuation. So I'm showing you an AC variation, although this is directly the shape depends upon the signal, AC signal which you have given. So this is reflected in the IC. Also, it is reflected in the VCE also. Okay, but the IB fluctuation will be very small Because IB, say for example, IB I'm giving a small voltage like this. This I'm showing the left part. But I'm getting bigger IC fluctuation in the collector part and bigger voltage VC fluctuations also. So this is, you can see the amplification action. Now this point is very important which you derived. This is the point. This is called Q point. It's called Q point. Quiescent point. This is called quiescent point. The point at which the transistor is fixed. DC biasing of transistor is fixed at the Q point. Here the Q point is 4 volt, 3 milliampere. VCE 4 volt, ICE is 3 milliampere. So this is in my Q point, quiescent point, right? Now about this Q point, my voltage is going to wiggle like this, increase, decrease, increase, decrease. So this is my constant or fixed DC point of my output voltage also, right? So at this point, my output current is also going to wiggle. This is the output fixed DC current over which my AC signal is going to fluctuate or swing. You can say swing. So this point is very important. Okay, I think this is you can see this is one example we have done. So I just shown the importance of the Q point, which is derived from the circuit. We can see some of the problems in the Malvino or the Bolstead, and you can try it. So all those things. So I'll repeat what we have done. This is the transistor. We have a RC, we have VCC, and we have IB, VB, right? So this is RB, and this RC. First, what we have found? First, we have found the IB. First, we need to find the IB. So we found IB. How the IB? We have the equation of IB. IB equal to VBB minus VBE, which is zero point 0.7 for silicon, divided by RB. This is we got IB. Now from the IB, if you got IB, if you know the beta, say beta equal to 300 or something, we can find the IC. IC equal to beta times into IB. Now we got IC. Now once we got IC, if you know VCC, there's 10 volt or something, we can easily find VCE. This is collector emitter voltage. So this is VCE. So we got the operating points of a transistor. How we see? VCE is nothing but VCC minus ICRC. So this is Kirchhoff law. You can see Kirchhoff. So we got VCC, VCE, and IC. This is operating point of a transistor. From this, we can right now tell what point my transistor is operating. For example, this is my transistor operating. Now here I plot my VQ point. This point. This is 4 volt, and this is 3 milliampere. So this is my Q point. What's important on Q point? Now, based on this point, my output is going to fluctuate. Maybe my output is going to change like this. My output is voltage is going to fluctuate like this. So this is a range, and current is also going to fluctuate. Maybe the current is fluctuating like this. So this is the range. Current fluctuation. So based on these ranges, I can get a line. So this is a fluctuation of my output. Right? So this is varying here, is varying here also. So this is much higher. This is variation is because of variation in my base current. Base current is slightly varying here, like this IB. So this variation will produce a greater variation in the output characteristics, voltage and current. Right? So this is ultimately the signal is amplified. Why? Because of the DC. We are operating or fixing the DC stable or biasing point of a transistor. If you fix the DC point of a transistor nicely, you'll get correct output. If the DC point is not fixed correctly, if it is coming in the saturation region, that is, if it is coming in the saturation region, the point is shifted to saturation region is very bad because we don't have fluctuation. Voltage fluctuation or brightness swing is very less here. Or if it is coming into cutoff region, also there is also very bad. So we should fix in the middle. So we should design the circuit in such a way that our Q point is exactly in the middle. What is the advantage? So that I have maximum swing. My voltage swing is maximum, current swing is also good. Else, if I'm in saturation or cutoff, my output will be clip, right? You know, clipping, output will be clip. My signal will be distorted. I don't get the proper amplification. So that means you can see there is when you are in near amplifier, you can see there is some cramped signal. So that is the problem. So again, we'll discuss. We have discussed common emitter configuration. The same things analysis can be applied for common base also. And now we'll discuss different biasing configurations. So again, I'll repeat, you should go through the datasheets. What is datasheets? We have different transistors. For example, NPN transistor, the best example is BC548 is one example of NPN transistor. And PNP, I think, is BC547 or something. I'm not sure. You can check BC. So you can go to the datasheets, download these datasheets, or you can see these datasheets in the internet, and you will see the current characteristics, voltage, power rating, the beta variation. The beta is also changing sometimes. So also the more designers have more challenge, more headaches are there in analog because beta may change, IC may change, everything may change. So your Q point also may change. It is not good, so you don't get proper amplification. So there are a lot of challenges of analog designer is we need amplification at the same time our signal has to be undistorted, it not be affected by noise, it not be clipped, it should be uh, perfectly uh, amplified in the output. Okay, so I think I'll stop it here. You can put your roll number. If any doubts also.